Our next topic is an alternative way to write the derivative, an alternative way to find the derivative. It's an alternate format. We have an alternate format for working with the derivative. In certain problems and in certain applications, and we've seen this already a little bit, this can get unwieldy. And in some problems, it is so unwieldy as to be problematic. And it turns out for certain problems, a different approach is actually better. We're going to develop that different approach and show that really it's the same thing. It's really just different notation. But by changing the notation and a little bit of changing our perspective, we see the same problem in a little bit different light and allows it for a little bit easier solution. So, first off, what we have here, this is the definition of the derivative that we've developed so far. It's the limit of this difference quotient. And here's the picture. We have a value of x. Now, when we're talking about this usage, this definition for the derivative, we're trying to find a function. Our final result is going to be a function. We want our final result to be a function of x. And that's one of the reasons we express this as a generic value, because there's nothing magic about this point. We could be finding the derivative at this point, or this point, or this point, or any point in the domain of this function, potentially. And so that comes into play when we're trying to find the derivative in a generic sense. There arise, however, circumstances where we don't want the generic definition of the derivative. We don't want the derivative at any particular point. We want to find the derivative at a particular point. And so that's where this alternate format comes into play. Now, what I'm going to do is this. I'm just going to change the notation. Remember in our picture, where is this notation in this picture? Remember from our work with the tangent line and the secant line? Remember what we said is we choose delta x. Now, where is delta x in my picture? It's not here. This is delta x. This point has coordinates x plus delta x. That value is that expression. So this piece corresponds to finding the function value here. And then once we have that, then we can find this point. And then from that, we have our secant line, right? And we find our slope of the secant line. We take the limit, and on and on and on we go. What are the coordinates of this point? Those coordinates are x, comma, f of x. What are the coordinates of this point? They're a little bit more involved here. I need some more space. The coordinates here are x plus delta x, comma, f of x plus delta x. So that's the labeling of the picture from the perspective of this notation. Oops. We're going to take a little bit different look. Suppose, and I'll write this in a completely different color here, suppose I want to find the derivative. I'm not interested in the derivative at any specific spot. I want to find the derivative at a particular value, a. So I want to let a equal this specific x. I want this x value to equal this a. So this x is this specific value of a. And now we have to change all this notation. Because if there is no x, there is no delta x. What I'm going to do is this. Let's just label this as a. And let's label this as x. Now, there is no delta x. There is no delta. It doesn't really come into play. But here's the key. Delta x goes to 0. We're taking the limit as delta x goes to 0. Well, as delta x goes to 0, what happens to this red x? As delta x is smaller, this red x is now over here. As delta x is smaller, the red x is over here. A is staying fixed. X is approaching a. So delta x goes to 0 is the same as x goes to a. So our new notation is going to be, we're going to take the limit as x goes to a, rather than delta x goes to 0. but it's a different notation for the same thing occurring. Now what happens to the rest of our notation? Well, what matters is these are no longer the coordinates because this is no longer x comma f of x. These coordinates change to a comma f of a. And this is no longer x of x plus delta x. This changes to x comma f of x. And for the slope of the secant line, instead of taking y coordinate minus y coordinate f of x plus delta x minus f of x, now for the slope of the secant line, we take y coordinate minus y coordinate. And so this numerator, f of x plus delta x minus f of x, that's the same as, in the red notation, f of x minus f of a. And so that's what goes in our numerator, f of x minus f of a. And then what is delta x? Well, delta x goes to 0, right? Well, where did this come from? Remember, this came from the change in the x coordinate minus x coordinate, x plus delta x minus x, and the x's fell out. But now I need to take this x coordinate minus that x coordinate. And there's no simplifying to do. This x coordinate minus that x coordinate, x minus a. And what we have developed now is exactly the same thing. So delta x is the same thing as x minus a. And so that gives us this new alternate format for the definition of the derivative. So I'm going to clear this out and sort of summarize the work we've talked about here. You may, if you wish, use this as the definition of the derivative. You may, if you wish, use this as the definition for the derivative. F of x minus f of a all over x minus a. But the difference is this. This is f prime of x. This is a function. Your result will be a function of x. Here, the result will be, this is f prime evaluated at a domain value. Your answer here will be a specific number. And so we should be able to get the same result no matter which of these two we pick. But this, and we'll see that here in just a bit, but this is one form for the definition of the derivative. This is another form. Typically, this is used if you are interested in the derivative at a specific particular value for some reason that will become clear later on. So if you're interested in the derivative at a specific point, this would be particularly useful. If you're interested in the derivative as a generic function, this would be particularly useful.